Morse potential. Consider a fictitious molecular crystal with a simple cubic Bravais lattice. Assume that each atom interacts only with its nearest neighbors through the following Morse potential. V of r equals V0, parentheses exponential minus 2 kappa r minus lambda minus 2 exponential minus kappa r minus lambda, where V0, kappa, and lambda are referred to as the Morse parameters. Part A, find the equilibrium lattice spacing A. Part B, compute the total binding energy of the crystal. Assume that there are capital N atoms in the crystal and that the total kinetic energy of the atoms is 0. Now, in order to find the equilibrium distance, we have to calculate the interatomic force. The interatomic force is equal to minus dV dr, and if we evaluate it at the equilibrium distance, a lattice constant r is equal to a, let's say, this should be equal to 0. So V of r is given, that's the Morse potential, V0 exponential minus 2 kappa r minus lambda, this is our repulsive term, and minus 2 exponential minus kappa r minus lambda, this is our attractive term. So if I take the derivative dV dr and evaluate it at r is equal to a, this will be minus 2 kappa V0 exponential minus 2 kappa a minus lambda, and then we have plus 2 kappa V0 exponential minus kappa a minus lambda, and this should be equal to 0. So we can see that this implies exponential minus 2 kappa a minus lambda should be equal to exponential minus kappa a minus lambda. So that means you can get rid of the exponentials. Minus 2 kappa a minus lambda should be equal to minus kappa a minus lambda, and we find that if I take minus kappa a minus lambda to the left hand side, minus kappa a minus lambda should be 0, which tells us that a is equal to lambda. So lambda is our equilibrium interatomic distance. Now part B, to calculate the binding energy, we have to evaluate the Morse potential at the equilibrium distance, that is V0 exponential minus 2 kappa lambda minus lambda, and then we have minus 2 exponential minus kappa lambda minus lambda, and this gives us V0 times, the first term will be 1, the second term will be minus 2, 1 minus 2, this is minus V0. So number of nearest neighbors in the simple cubic lattice, so we're given that this is a simple cubic lattice, that's the coordination number. Coordination number is 6. So for one atom, we have a binding energy of minus 6 V0. And for capital N atoms, we need to include 1/2 to avoid double counting. And we find that the total binding energy will be capital N over 2 times minus 6V0. So we will find the total binding energy to be minus 3N V0. So this will be the binding energy. All right, so we're talking about the Morse potential, a fictitious molecular crystal with a simple cubic Bravais lattice. Each atom interacts only with its nearest neighbors through the Morse potential. And we want to know the equilibrium lattice spacing, so we look at the interatomic force, the minus the derivative of the potential with respect to the distance between atoms evaluated at the equilibrium distance. This gives us an equilibrium distance of A equal to lambda, one of the Morse parameters. And in part B, we need to compute the total binding energy of the crystal, assuming capital N atoms in the crystal, and zero kinetic energy. So we have the potential, Morse potential for a pair of atoms, basically at a distance, equilibrium distance A is minus V0. And so for number of nearest neighbors in this simple cubic lattice, we have 6. So for one atom, we have a binding energy of minus 6V0 if we pair it with the 6 nearest neighbors. For capital N atoms, we cannot just multiply it by capital N because these are coming in pairs, so we have to divide it by 2 to avoid double counting. So this gives us a total binding energy of minus 3 capital N V0.